Any questions before we get started? Any questions about lab this week? Good to go? Any last questions about test 1 material? Good to go? Test 1 on Monday. Format is similar to Organic 1 with me, which is we have topics. We have nomenclature of alcohols and ethers. We have reactions of alcohols, reactions of ethers, including epoxides, including multi-step synthesis, oxidation of alcohols, and oxidation of alkenes, and NMR, including comprehensive spec problems. Examples are in the workbook there. You will see a comprehensive spec problem on the test. Okay. New material, new handout. One white one. And one green one.
Thank you so much. I really appreciate it.
So this week in lab, we're doing our first aromatic reaction. Using sulfanilamide as starting material, you'll be halogenating it. Either chlorination, bromination, or iodination, yeah. And then starting next week is our 8-week lab, which focuses on fluorine. Not chlorine the element, but spelled with an E. Fluorine is an aromatic ring. Aromatic hydrocarbon, and the first reaction we will do is nitrate fluorine. So that begins next week.
Quick question.
Yeah.
In the article you sent yesterday, it talked about Faraday passing benzene through a red hot tube. I'm just curious what that is.
Perhaps combusting it,
That's, okay.
burning it, converting all the carbons to CO2. And that's probably how he determined the empirical formula. He got the empirical formula wrong. I believe he said it was
C2H.
C2H instead of CH. He thought it was double the amount of carbon. Well, that's because back then they thought the molecular weight of carbon was 6, not 12. So in order to get a certain amount of carbon, you had to have double the amount to equal, well, so he wasn't wrong, they were wrong. The chemical community at the time was wrong. He actually got it right. Yes. You can determine empirical formulas from percent composition. Percent composition has come from combusting the compound. So I imagine that's what was going on there. Okay, with aromatic compounds comes aromaticity. What is aromaticity? What is an aromatic compound? Okay, there's some warm up here. 2 different handouts. And one of them, I think the white handout in the back, last page, aromatic nomenclature. Okay, that will be covered by video only. I need to create that video likely today and I'll get that posted. Okay, aromatic nomenclature. Green is our outline. White is more of the show and tell. Just a reminder, drugs. Look at every one of these drugs contains a heterocyclic ring. Planets, benzene rings, granddaddy of aromatics. But it also contains a thiophene ring, which is aromatic. And a piperidine, which is not aromatic. So in addition to hydrocarbon benzene, we'll be looking at aromatics that have a heteroatom. Heteroatom meaning non-carbon, something different, so something other than carbon. Most common heteroatoms are for rings are sulfur, oxygen, and nitrogen. For example, a pyrrole ring, 5-membered ring, 1 nitrogen. Lipitor has a pyrrole ring. Aromatic, it also has several benzene rings. Okay, some of those names we will learn. Okay, intro to benzene and aromaticity. All right, this is test 2 material. Will not be on test 1. Benzene is a liquid, formula C6H6. Okay. Yes, the empirical formula is CH, not C2H, but it's C6H6 in terms of the actual formula. All right. Benzene has this structure here, 6-membered ring, 3 pi bonds. You have seen it many times. It's a liquid. Okay. Boiling point 80 degrees, water being 100, so it's lower boiling than water. It's actually a pretty good solvent. Okay? It's just hydrocarbon. But because of the pi system, it's a better solvent than such like hexane or cyclohexane. The pi system gives it some polarity. And you say, well, is it polar? Well, because electrons can be perturbed. You do this all the time. Induction. Okay? Pi electrons are more easily induced than sigma electrons. So because it's pi electrons, it's more sort of, the electrons are more inducible. It helps it become a better solvent, even though it's a hydrocarbon. The problem is it's got a nasty habit of being a carcinogen. Known carcinogen. Thus, it's not used in industry. It's outlawed in industry large scale. Okay? I used to use it a little bit, recrystallizing a couple of compounds when I couldn't get some other solvent to work. I don't use it anymore. It used to make my arm hurt right here a little bit, muscle something. I don't know what it was, but I'm not going to use it anymore. Toluene, though, is a little bit safer. First isolated in 1825 from well fat. They used to burn well fat in the lamps, like in the streets or homes. And from this residue, somebody, I don't know who, was able to isolate benzene. Who was it? A guy named Faraday actually was the first to isolate benzene out of this residue that came from well fat. Well fat's a source of natural products, and it was pyrolyzed and briefly in all these other organic molecules created from decomposition, etc. The well probably doesn't have this benzene floating around, but the stuff that is in the well fat, when it's quickly pyrolyzed and degraded, it can form benzene. The structure of benzene, even though they knew it was pure, they had it, they didn't even know what the structure was for a long time. It wasn't really confirmed until the late 1800s. The double bond was not even proposed until the 1860s. Okay? So basically back then they knew it contained carbon and hydrogen. They knew it was a hydrocarbon. A lot of early structures were proposed. There's one on the right. There's no pi bonds. It does have the correct formula and the correct DUS. Basically three cyclopropanes sort of connected to each other like that. There were There were several other structures proposed. That compound was actually made later, like in the 1960s. So that compound has now been made. It's not the same as benzene. It's got different properties. It's given a name. But benzene is known to be this structure. Okay. Let's look at the structure. Each carbon is sp2, trigonal planar with 120-degree bond angles, right? sp2, of course, means this. What type of bonds do you see this carbon making? There is H on each carbon, okay? 3 sigma bonds and a pi bond. All right, 3 sigma bonds using your hybrids. Sigma bond to carbon, sigma bond to carbon, sigma bond to hydrogen, and then a pi bond to carbon, with this being a double bond, right? Each carbon is the same. We can look at so-called the sigma framework, where we just look at the sigma bonds. All right. Each carbon is the same. Trigonal planar. The geometry comes from your sigma framework. Your hybrids, sigma bonds. Trigonal planar, 120-degree bond angles. And then each carbon has a p orbital. And we can put that here and show p orbital overlap to make pi bond. Or we can kind of show the p orbitals separately. Each p orbital has 1 electron. And so these can overlap, these can overlap, and these can overlap to give you 3 different pi bonds. On the other hand, instead of saying these 2 overlap to give pi bond here, how about we say instead these 2 overlap to give pi bond there? Which is it?
Combination of both.
Which is it?
It's either.
Both. There is continuous overlap. There's pi orbital overlap all the way around. Okay? We conventionally or typically draw the structure either this or this. Those are resonance structures. Neither one is strictly correct. All right? Because there's just as much pi overlap between these 2 carbons as these 2. Okay? So both are right and both are wrong. The true structure is a hybrid. The hybrid is going to have pi overlap all the way around. And it's actually going to be, okay, these are resonance structures. Double-headed resonance arrow. We can get between them by, on the board or on our paper, move these down. Move these over here, and move these up here. That's going to give you the resonance structure. Question?
So this is it's dynamic. It's moving, correct? Due to resonance.
Well, we've covered resonance before. I never used the word dynamic.
Is there any intrinsic rotation to that?
Do what?
Is there any intrinsic rotation or movement of the pi bond in the benzene rings?
You got to be careful. It can be induced by a magnetic field, and you can get anisotropic effects in NMR, which are covered in the NMR handout. You got to be careful about moving. The answer is yes and no, but you got to stay out of trouble.
Okay.
And don't do the no part. Resonance is not anything moving. Resonance sounds like going back and forth or something. I don't know if that's what you're getting at. Some people have said resonance is a bad term because it sounds like something's going back and forth. No, it's just there. You got pi overlap all the way around. That's it.
Okay.
But we don't typically show, just like hybrids, we don't show hybrids with all these partial bonds because it gets cumbersome. We show fake structures and say, hey, do you understand the idea of resonance? The true structure is somewhere in between. It's pi overlap all the way around. If you could take a picture of benzene, the electron density is all the way around. Bond order. If it was one of these structures, it looks like double bond, single bond, double bond, single bond. And you would expect longer bonds. A single bond is longer, known to be longer, like 1.5 angstroms. A double bond, carbon double bond, 1.3. So if it was double, single, this would be an ugly looking 6-membered ring. Short, long, short, long, short, long. We know benzene is not an ugly looking ring with alternating bond lengths. It is a perfect hexagon. Each carbon-carbon bond is 1.39 angstroms. That's rounded off. That is basically right between single and double. Perfect hexagon. Because the bond order all the way around equals what? 1.5 all the way around. Coming from your high, what's the average of a single and double? 1.5. Which is a major resonance structure? Equal contributors. They're the same. So it's a perfect blend, 1.5 all the way around. This is more what benzene looks like, not like that. Because of this, now this is supposed to indicate half bond, bond and a half, bond and a half, bond and a half. Okay, I just drew it sort of circular. Now, a lot of people, as shown below, will actually draw benzene and just do that, indicating that it's fully delocalized. I would never do this, okay? Never do this, because if you ever start doing mechanisms, how are you going to do a mechanism with a circle? I just would never do that, okay? And you'll never see me draw benzene like that. I prefer to draw one of the fake structures, which is, look at any of my handouts, they all have the fake structure of benzene. The isolated, okay? You got to understand resonance, you got to understand what structures here. We will use this term going forward a lot. It is a fully cyclic conjugated system. Okay, that's written somewhere. We'll say that a lot. By the way, a guy named Kekulé, chemist, 1860s. At this point, they were sort of, okay, we think the structure may be this. Some other people still argued it was some other structure. Okay. By the way, Kekulé was, I think, maybe the first to propose this structure for benzene. I think. I can't keep it straight. But he also thought that you could get isomers here. Dibromo, or two substituents. You should be able to get one compound where the double bond is between the substituents, and then you should get another with it's not between the two substituents. And he actually tried to isolate these from dibromobenzene. There's got to be a mixture of these. And guess what? Even though he tried real hard, he never could isolate these two. Because it's the same compound. It's neither one's correct. The true structure is this. Okay? It's fully delocalized through there. It's just one compound. All right? So I reckon he finally gave up. And all right? Okay, how do we know that the bond lengths are the same and bond angles? X-ray crystallography, very common these days, even though you don't probably see it much at the undergraduate level. Here's an X-ray structure of a compound we made in the research lab, fluorinating this. We didn't know what we had until we got X-ray. Here's an X-ray structure showing the structure. You can see in the crystal structure, if this ring is planar, flat on the board, this one, you see how it's turned? You can see the 3D nature there? It's turned relative to the other one. Okay? You can see things here. But you can also see determined bond lengths and bond length here, C1 to C6, that must be right here, this bond length right there. Okay, bond lengths can be determined by X-ray, also bond angles. Okay. I don't know what bond angle that is. Oh, here it is. It's got to be 3 to be an angle. It's to the chlorine. No, did that say Cl?
Yes.
Is there chlorine? Okay, there's a chlorine over there. That bond angle right there is the angle they're talking about. So that's not really a carbon-carbon-carbon bonding of the ring. Is there one of those shown? But you still would expect 120. I mean, every angle around this C1 should be 120. But do they have a C6, C1, C2? Basically, you can look for it there. What I'm trying to get at is bond lengths and bond angles can be readily determined these days through something like X-ray crystallography. Okay? Now, assuming your compound's a solid and it can give suitable crystals. Now, benzene is a liquid at room temperature, but at cold temperature, it's a solid. It will freeze, and as Faraday said in his paper, it forms. I think he used the term dendritic. I can't even pronounce it. I don't know the word. I want to say dendricular. That doesn't sound right to me. Basically, when benzene freezes, it forms little needle shards looking. Keckerle saw this in the 1820s. You can see it today by chilling benzene. Okay. As we go along over the next day or two, we'll give a more involved definition of aromaticity. Right now, we can say aromaticity is an unusual stability as a result of full cyclic conjugation. Hopefully, I just explained that benzene has full cyclic conjugation. What does that mean? How do you recognize full cyclic conjugation? It's cyclic, so it has to be a ring. Full conjugation. It's fully conjugated. What does that mean to you? Can you recognize fully conjugated?
Around the entire subcircle.
Uh-huh. Cyclohexane, is it fully cyclic conjugated?
No.
No, conjugation is p orbitals, right? Okay. Cyclohexene, is that fully cyclic conjugated?
No.
No. What about cyclohexadiene? Is that fully cyclic conjugated? No. What about this? I reckon we call that benzene. Is that fully cyclic conjugated? Do you know what it means? Okay. P orbitals on each atom all the way around the ring. And the p orbitals are interacting. But just because they're side to side doesn't mean necessarily interacting. What if they're like that? They're not conjugated. Okay. But this leads to an unusual stability. What do I mean by unusual stability? Experimental evidence for delocalization. B. What was A? How do we know it's aromatic? What was A?
Bond angles.
Bond angles. Okay. Because if it's got to be sp2 to have a p orbital, and if it's sp2, it's going to be 120. Bond angles, right? That's what we're talking about. Can you determine bond angles? Yes, that's the purpose I just showed you. How? X-ray. Since we can determine it, let's call it experimental evidence. X-ray crystallography can be experimental evidence for determining aromaticity or delocalization. What is another way? What is other experimental evidence? What about reactivity? If you react benzene, you try to react it with bromine, you may think, well, we got a pi bond, we can do an addition to the pi bond and maybe get something like this, transaddition of bromine. That's how bromine reacts with pi bonds. It's a trans or anti-addition of bromine. Well, guess what? Benzene doesn't do this. Cyclohexane would do this, but not benzene. No. Instead, bromine reacts, or benzene reacts with bromine to give a substitution product. one of the H's is replaced with bromine. And we actually make HBr, that's the fate of the other bromine. It undergoes a substitution reaction instead. So this tells us it's different from just a regular old alkene. Alkenes undergo addition reactions with bromine. And by the way, it doesn't react very easily with bromine. You have to include a catalyst, such as iron. So it's more sluggish to react. When you brominated transtylbene in organic 1 with mead, it reacted instantly, almost like a titration. Benzene doesn't. And it gives us, so it has an unusual reactivity. This is also common for aromatics. Aromatics react this way. If it was not aromatic, it would typically do that chemistry. We know alkenes, you can oxidize them with like osmium tetroxide, right? And make like a diol. Well, guess what? Benzene doesn't react with osmium tetroxide. Benzene is not just a compound with 3 alkenes, because it doesn't do typical alkene chemistry. It's got different reactivity. I'm saying unusual, or we can say different reactivity than alkenes. And again, this is common for aromatic. If this was not aromatic, there would be no reason it would not react with this reagent, because pi bonds react with that reagent. Heats of hydrogenation. What can it tell us? What can this experiment tell us? We know if we hydrogenate an alkene with hydrogen and like palladium or platinum or something, we can reduce it down to the alkane, 2 H's added. If we add H's, that's a reduction, right? Okay, so we're reducing the alkene to the alkane. We know this is an exothermic reaction because we're replacing a pi bond with 2 sigma bonds. We've covered that before. And so we expect heat to be generated, and you get 118 kilojoules per mole in that reaction. If you take the diene and do the same thing, you would need 2 equivalents of hydrogen here. We can reduce all the way down to the same product. So you get 230 kJ per mole. First question, why do you not get exactly double? Double would be 236. Why do you not get 236? Why is it only 230?
It's more stable in the first one. There's 2 pi bonds, so it's more stable initially.
Why is it more stable? Let's compare that to this. Is there a difference? That's a cyclohexadiene. That's a cyclohexadiene. Is there any difference between the two? Which one's more stable? More stable, what? Conjugated. Yeah, this one is closer to 236. Double of 1, it's got 2. Why is that one less exothermic? Because this is more stable. It's lower energy because of conjugation compared to this one. So it's not exactly double. What if we take benzene and hydrogenate it? Well, you need 3 equivalents of hydrogen here. You also need a much more active catalyst. Palladium is not active enough. You need to go to more expensive. Well, maybe not more expensive, more rare, and probably more expensive. Over here, rhodium, iridium, these tend to be more active for hydrogenation than these 2. You also probably need some high heat here, which is not shown. Basically, it's tougher, harder to hydrogenate. But it can be done. We can fully hydrogenate. But look at this. It only releases 205 kJ per mole. Well, that's not triple. And you get less here than here. What does that imply?
It has a lower energy source.
This is lower energy than that. Even though we have more pi bonds and less sigma bonds. Why?
It's the conjugation.
Fully cyclic conjugated. And the fully cyclic conjugated is a magical thing that stabilizes the compound. And this stabilization, all this is called aromaticity. It's aromatic. And the difference between triple this would be 354. We don't get triple. We only get 205. The difference, 149, could be said that's the amount of stability that's in benzene. Compared to if it was just 3 alkenes. Benzene is not just 3 alkenes. It's a special cyclic conjugation that leads to unusual reactivity, unusual stability. We can see the stability experimentally by doing like H of H. That can give us numbers, quantify it. Again, if this was just 3 pi bonds, we'd expect 354 when you did this experiment. But it's not. What's another way we can study aromaticity and determine if a compound is aromatic? What about NMR? Because hydrogens on alkenes are typically 5 to 6 ppm. But on benzene, they're about 7 to 8 in general. If this was just 3 alkenes, these H's should be 5 to 6. So again, this is experimental evidence. What leads to this H being more downfield? Anisotropic effect. Yeah? Turn over a couple of pages. Diagram here, we showed this in the NMR. Benzene. The H sits out here. The magnet will induce a current with the electrons. Okay? And those electrons, because they are fully cyclic conjugated, I think the current is larger. Since the current is larger, that's what leads to the more downfield. Okay? And the current, well, there's multiple things here, and sometimes my knowledge here can break down, but I think the current creates its own magnetic field. So you got an induced thing that then induces something else. So, okay, but the induced field from the current is known to, well, I think there's a rule in physics, because if you induce a current, it's going to be oppose the original. There's something like that in physics? Look for it. All right? But in any event, it's circulating, and it's known to come this way. All right? It's all physics. But out here where the H is, this current is adding to the magnet current. Out here where the H sits. And if we add to it, is that a shielding or de-shielding effect? Shielding. Because removing current would be like removing sunscreen. You remove sunscreen, that's de-shielding. Okay? And no, that doesn't sound right, does it? No, let's go back. Let's think for a minute. We're adding to it, so it gets more current, right? We're adding to this. Like getting more sun. Well, that would be like removing sunscreen. And that would be like de-shielding. Yes. And de-shielding in the NMR leads to the signal being more
Downfield.
downfield. That's why the peaks are 7 to 8, more downfield than like 5 to 6. Yes. I think the answer is basically because it's aromatic, I think this current is greater and leads to more of, it makes this greater and thus a more downfield effect. The large aromatic induced current. This is not right, is it? It's de-shielded, isn't it?
Yeah.
Yeah, that's not right.
Is it showing the difference between paramagnetic and diamagnetic? Is it up the top it says it creates the opposite effect? If it's paramagnetic?
Hold on. I have to figure out what this is saying. No, it's de-shielded. That's correct. What am I saying here? Which way is this? This is a diamagnetic current, right? Why did I say this? 'Cause this peripheral edge is shielded by paramagnetic.
There's a picture below that.
Okay, I'll take this back. This is correct. This is referring to something else. Right there, somebody checked it. This is what we were talking about. This is referring to something else. Sorry, guys. Okay, we'll see where that comes in. I reckon I was looking at this. That kind of confused me. It was like this is pointing up here, but that's what I drew. Okay, make sure you understand that. Sorry for the confusion. Everything is clear here. The proton is de-shielded by the induced field, but it's adding to the B naught. Down here, this is something interesting. This is an aromatic compound. Large, we'll be looking at different sized rings like this. With benzene, all the H's are on the peripheral. There's no H's in between. Can you have H's in the middle of an aromatic? Yes. You see how these H's are in here? Two signals for this compound. All H's out here are one signal. These H's are another. These H's in here actually give a peak at negative 3.0 ppm. Negative 3. I thought aromatic region was 7 to 8. It is for peripheral. Why are these in here at negative? That implies that there's lots of shielding or de-shielding going on.
Shielding.
Good, lots of shielding going on. How's the shielding going on? If you go back up here, what if there was an H sitting in the middle here? Right? If the H is sitting in here in the middle, you experience shielding. Because there, the induced magnetic field here, generated magnetic field, is opposing B naught. And that's a shielding effect there. And it's a very substantial shielding effect. And you actually get a negative value. Okay? That's a rare example. So that's why it's never going to appear in like the tables. Okay. But what you should do is you should say, okay, this all is starting to make sense. I'm seeing examples of how we can have de-shielding and shielding. And by the way, the de-shielded signal is, you notice it, 9.3? That's also not 7-day. That's pretty de-shielded. That's because there's such a large pi system here. So it's going to extreme to both ways, kind of. Okay, so in the end, NMR can also be used to study aromaticity. And we'll be referring to these experiments along the way as we look at different examples. And say, okay, how would you determine this? What data might we collect? Because again, this benzene here, I can look at it all day, but you need to collect the data if you want to understand the molecule, right? Right? So what type of experiments and data can we collect? Okay, key to drawing molecular orbital diagrams, nomenclature. Let's look at the other structure of benzene. All right. Now, Roman numeral 1 and 2 we have done. That's what we just did. Roman numeral 3. Let's compare benzene to cyclobutadiene. You will see plenty of other rings. Cyclorene, 4-carbon diene, cyclobutadiene. Okay? Benzene is a common name. A more IUPAC name would be cyclohexatriene. 3. Okay. Let's just call it benzene. Cyclobutadiene. Okay? Very stable. Very unstable. Very unstable. Why? What do we mean by unstable? It only exists at very low temperature, like minus 100 degrees. If you give it any heat, it's going to react. It'll dimerize. It self-reacts and turns into something else. Sounds like it's not a happy camper, is it? Not that stable. Yeah. This is known to be aromatic. This is known to be anti-aromatic, which is just the opposite, very unstable. Is this a cyclic conjugated system, fully cyclic conjugated?
Yes.
Yes.
It is. It has a p. Every carbon has a p orbital. And you show the p orbitals, 1 electron each, all 4 interacting. Yes. Both are fully cyclically conjugated. So hold on. We kind of almost said that fully cyclically conjugated led to aromaticity. Didn't strictly say that, but you may have been thinking that. Clearly it doesn't. Well, it kind of does. Both have to be fully cyclically conjugated to have this part. But why? Why does that have the anti part? Why is it, okay? We need to look at that. Aromaticity is an unusual stability due to full cyclic conjugation. Anti-aromaticity, an unusual instability due to full cyclic conjugation. To understand what's going on here, we need to be able to do molecular orbital diagrams. And that's what we're going to do. I did not do any of this in Organic 1. I told you oxygen is sort of, maybe I told you this. oxygen is paramagnetic, but Lewis structure doesn't explain that. You have to do an MO diagram of oxygen to see why it's paramagnetic. Okay, let's do MO diagram. Let's kind of start with butadiene. Okay. Now we're going to do MO diagram of the pi system. How many p orbitals here?
4?
4. Okay. How many pi electrons? Also 4. Okay. Molecular orbital. This is an orbital that's spread over the entire molecule. Usually we just talk about atomic orbitals. When we do hybridization, we're taking a regular orbital, atomic orbital, and we're hybridizing it and creating a new atomic orbital. Hybridized atomic orbital. We're going to create molecular orbitals. This comes from interacting, it's largely based on math, okay? But it's math that supports observation and generates the theory. The 4 p orbitals here can all interact in different ways. I'm going to draw this a little bit lower. They're all here. And I'm just going to kind of go through this, and then we'll kind of maybe step back and explain again what we need to. These 4 orbitals can interact all together. All same phase, interaction all together. And this sort of implies all good interaction. But once they're all interacting here, this is one MO. And interaction of all these generates a new orbital. But it's an orbital that's spread over the entire molecule. You know how we do hybridization? We mix a S and a P. We're mixing 2 orbitals, and we make a new one called SP. But it's still an atomic orbital. It's still just on one atom. Well, here we're mixing 4, and it creates one new orbital. We don't really give it a name, but we say the new orbital is over the entire molecule, as opposed to just sitting on an atom. And that's just one MO. We can get another orbital, another MO, by combining these in a different way. Another way they can combine is, instead of me drawing the orbital and putting the sign in, can I just put the sign?
Yeah.
What about if we had plus, plus, minus, minus? Then these would be interacting, and these would be interacting. Okay? I just didn't draw in the orbital just to save some ink. But between this one and this one, there's no interaction. And so we can indicate this sort of with a line here, and this is called a node. A node is a plane where there's no electron density. We'll call that first. And this is your second MO. And this is higher energy. Because this orbital has overlap with every atom in the molecule. Here we have a node, and it's not as much overlap. Okay, we can get Now, there's some rules. I got golden rules in the handout here. If you want to take a look at it, I would recommend that. But one thing you'll see here, as we go up, we get more nodes. This has 2 nodes. And the nodes can actually help you put in your signs. 2 nodes. So if this is plus, what is this going to be?
Negative.
Negative. And what is this?
Negative.
Negative, because I'm showing overlap here, and this is
Positive.
plus. And this is a third MO. And it only has there. And then the fourth one, I'm not tall enough to do the fourth one, but it has 3 nodes. And if this is plus, this is minus, that's plus, that's minus. Fourth MO. That should be at the top. Okay? We're going to finish this up in 1 minute. And that one looks pretty high in energy, would you agree?
Yes.
I mean, there's no interaction there of any of the orbitals. That's sort of the highest energy possibility. What we have here is we have 4 energy levels. How many electrons we have? 4. You put them in here just like you do with anything. Off-Pauli principle, Pauli exclusion principle. First electron goes here. Where's the second one go? Here, here, here. That is, 2 electrons sit in this orbital, a molecular orbital, and 2 electrons sit in this molecular orbital. Ground state. At ground state, no electrons are in this orbital, and no electrons are in that orbital. Okay? By the way, we have right here out of time here, guys, but this is, we'll have to maybe redraw this. This is a bonding MO, anti-bonding MO, anti-bonding MO. That comes from the bonding interactions. Bonding interaction, bonding interaction, bonding interaction. 3 bonding net. Bonding, bonding, but no. So 2 bonding and 1 not. That's like 1 bonding net. Both of these are bonding. If you look at this one, it's called anti-bonding, anti-bonding, and only 1 bonding. So what's the net?
Negative 1?
1 AB net. You see, that's an anti-bonding molecular orbital. What is this?
All anti.
3 AB net. We got 2 bonding molecular orbitals net, 2 anti-bonding. Of the 2 bondings, that one's better than this one, because this one has more bonding than that one. This is an MO diagram of butadiene. We'll pick up here on Friday. Have a good day, guys.